Ow!
Newton's laws of motion, or laws of motion, by Marcello Pavino and Bowen Liu. Newton's first law states that for every object will remain at rest or in uniform motion unless acted upon by an external force. This tendency to resist change in the state of motion is known as inertia. Newton's second law states that the acceleration of an object is directly related to the net force and inversely related to its mass. Acceleration of an object depends on two things, force and mass. This law follows the equation F equals ma. Newton's third law of motion states that for every action, there is an equal and opposite reaction that have the same magnitude but opposite in direction.
Ouch, that looked kind of painful, but was it actually? Today, we will be calculating the force in newtons, of course, that anvil bonked that guy on the head with, along with talking about the 3 laws of motion created by Isaac Newton himself along the way, with, of course, guest appearances from very special individuals to help you guys kind of understand the laws. First, we must find the acceleration of the anvil, using, of course, the gravitational acceleration of Minecraft's Earth, which can be found by using this funny little equation on screen and, of course, filling in the variables of distance and time, which we will find in like 2 seconds. Luckily, we can find these 2 variables by running a funny little experiment where we know the distance and all we have to find out is the time to find acceleration. As you can see, we made a little anvil drop around 20 meters, and of course, we know the time. So we just plug it into the equation and we'll get our acceleration. As you can see, I've already done all the math and stuff and found that the acceleration was 13.84 meters per second squared, with of course the time being 1.7. Now we could go ahead and calculate mass and whatnot, but first we need to talk about Newton's first law with our very first special guest.
This is for my homies Marcello Pereno and Bowen Louis. Newton's first law states the following: all objects are constant in velocity without an unbalanced force acting upon it. This change in motion could be caused by a push or pull, and this change will remain constant until another push or pull. All objects resist this change, which is called inertia. It not only dedicates itself to preventing motion, it also uses mass to do so. The more mass, the greater the inertia.
The question is, how could I showcase Newton's first law in the real world? Oh, a home. See, a perfect example is like a house, because houses have a lot of inertia. I mean, they're big, they have a lot of mass. So I can't push a home because it has so much mass. But this flashlight, which you can't really see, that I'm holding, it has very little mass, along with this little donut thing. With just a little bit of force, I can kick it around and move it as it goes into the darkness.
Newton's first law is also known as the law of inertia. Inertia is an object's tendency to remain unchanged, especially with respect to its motion. With here I have 2 different objects, and with 2 different masses. Inertia is based on mass, where the higher the mass, the higher the inertia, and because of that, this book has a much higher inertia than this piece of index card. And because of that, this book has a higher and stronger tendency to remain unchanged with respect to its motion. And this can be seen with this little demonstration here. So using a relatively low amount of force, I can move that index card pretty easily. Now with this book on the other hand, even with using more force just now, it's still pushed more harder and slower in comparison to the index card. And that's entirely due to the fact that the book has higher inertia, making it harder and more difficult to change its motion.
time to talk about Newton's second law of motion with, of course, another special guest.
In this video, we will be talking all about Newton's second law. Newton's second law is all about that motion will only change if a net force is applied. Net force causes an object's velocity to change and causes it to accelerate. When an object is acted upon by a net force, the change in velocity will be in its direction. This acceleration is very dependent on mass. The more mass something has, the more inertia and a greater force that is required to accelerate it. The same force can result in different acceleration depending on the mass of an object.
Newton's second law gives us two really important relationships. One is that force and acceleration are directly related, which means that an increase in one will cause an increase in the other. This can be seen here by pushing this object. Lower amount of force, high amount of force. As you can see, more force led to more acceleration. The second relationship that Newton's second law gives us is that acceleration and mass are inversely related, which means that an increase in mass will cause a decrease in acceleration. And this can be shown here by pushing these two objects. I will push these two objects with the same amount of force. The main difference is that these two objects have different amounts of mass, where this one is a lot higher. So, okay, same amount of force. As you can see, with these two objects, this object pushed a lot slower. It had much of a lower acceleration due to the fact that it had much higher mass, showing the relationship that mass and acceleration are inversely related.
Now to showcase a perfect example of Newton's second law, where force equals mass times acceleration. As you can see in this example, the telephone pole, which had a greater mass, had a lot less acceleration when applied with the same amount of force as the group of individuals who had much greater acceleration due to their lower mass. Now, how does this second law apply to our anvil situation? Well, as you may have guessed, thanks to our brilliant calculations, the anvil has mass. And because we've already calculated the acceleration, we can calculate its force. Well, the force of impact, of course. But first, I must retrieve something. Now that we have found the acceleration of our object, we must find its mass in order to properly fill out our Fermat equation from Newton's second law. To do this, we must find the anvil's density and its volume. But of course, we already know the density of iron, which I'll put on screen now. But to find its volume, we'll have to look at its in-game crafting recipe, in which it is made out of 3 1 cubic meter blocks of iron and 4 1/9 cubic meters ingots of iron. After completing some painful math, thanks to the funny equation on the little screen right now, we have calculated the anvil's mass, and since we've already found its acceleration, we can calculate how many newtons of force it will have. But we'll calculate that and talk about that that stuff after we talk about Newton's third and final law.
For every action, there is an opposite and equal reaction. When an object exerts a force on the second object exerts a force onto the first object that is equal in magnitude but opposite in direction.
The force exerted by the first object is the action force, and the second force is the reaction force.
Newton's third law says that for every action, there is an opposite and equal reaction. And this can be seen by dropping this ping pong ball. As you can see, dropping the ping pong ball, the action was the ball hitting the table. The equal reaction was the force that was put onto the table, while the opposite reaction was the force being put onto the ping pong ball, causing it to bounce back. You might ask yourself why the ping pong ball doesn't bounce 100% back to where it started, and that's because the ping pong ball isn't 100% elastic, meaning that as the ball hits the table, not all of some of the energy is lost, such as heat, for example. And yeah, this is a demonstration of Newton's third law.
A secondary demonstration that we will be performing shortly is honestly quite perfect when it comes to real-world examples. Now, obviously, we can't do what we're allowed to do in the real world because that will cause, real-world injuries. But as you can see, when the vehicle impacts the second vehicle in a car crash, the reaction force by the vehicle that we hit is to kind of knock our vehicle around, Our action force is hitting the car, which as you can see kind of moved a little bit, and then the reaction force was the car kind of hitting us. And yeah. Now that we have found the mass and the acceleration, we can calculate the force of our object as seen above. We did this by plugging in our numbers into the Fermat formula that we discovered near around Newton's second law. But of course, it is now time to calculate the amount of acceleration that the object experiences after it gets hit by our little anvil. Now, to find the final acceleration of our impacted object, which is like the little player, we need to find its mass, which was around like 100 kilograms, including the equipment that the little clone trooper would have worn, because we used a clone trooper skin. Now, this would obviously equal to a ton of acceleration, as you can see on screen. That would most certainly kill pretty much anything, but especially because it's an impact to the head, which if it was actually done on a human, would most certainly turn its head into atomized dust, like Thanos' Infinity Stones. Alright, thanks for watching, guys. I hope you learned something about Newton's 3 laws. I was going to do a little demonstration with a mini anvil and a pumpkin, but sadly, all I could find was this vise. I don't really have anything to drop, except this little like mini pumpkin thing. So, oh my, I can only do this once. So if I mess this up with my words, it sounds a little funny. Just ignore that. All right, it's got like mold on it, and I know that like it's kind of weird to drop a vise on a pumpkin, but yeah. All right, here we go. Yeah, I mean, what did you expect? Yeah, that's the demonstration for how that would go if you got hit in the head with an anvil from 20 meters. It's gone, okay? Your skull would probably be crushed like that, and you would die. Special thanks, this is like the outro as well, to Bowen Liu for being my partner in this. He did very important behind the scenes work. Special thanks to my brother. He was the one who dropped the anvil on my head in the little Minecraft thing. Credit goes to Obama, Mr. Beast, for those 100% not AI guest appearances. Is my face even showing here? Yeah. Thank you guys for watching. Sorry that like this sucks. Okay, bye.